Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Let's get started. We're very pleased to have Radu Yosef here with us today. He, in fact, is going to be here for the next 3 days also until Friday, and he'll come around to talk to many of you. Radu works at the Verimag lab, which is a lab in France, which is part of the national research organization in France called CNRS. And Radu has done lots of work on model checking and static analysis for programs. More recently, he's been interested in static analysis for heap manipulating programs, and that's what he's going to tell us about today. Okay.
Okay, thank you for the introduction. So, so now if you look at the title, it's not really static analysis, but it's something that might have applications to static analysis. So this talk will join two works that we did. So the first part is based on a FOSSACS 2005 paper, and the second part is something that we did recently, which is the application part. But the first part is purely about the first order integer arithmetic. And this is, I would say, the main topic of this talk. So what is the first order arithmetic? So it's the first order logic interpreted over natural numbers with symbols. So the logical symbols are the addition and multiplication. Then you have constants 0 and 1. Yeah? And you have variables, logical variables that you quantify existentially and universally. And they are interpreted over natural numbers. Yes. And so this theory is the mother of arithmetic, because basically any other arithmetic operation you can imagine can be written using only addition and multiplication. In fact, even powers of like x to the power of y can be even written like this using first order formulae. This is not trivial, but it has been proven. So anyway, this theory has been shown undecidable since 1936. It's quite an old and basic result. It's a direct consequence of Gödel's incompleteness theorem, in fact. And now people after that have been started to look at subtheories. Okay, so let's find something that's decidable in here. So one such subtheory is the subtheory of addition and divisibility. Okay, so divisibility means f divides g if there exists some x, such that f multiplied by x equals g. Okay, so just an integer divisibility predicate. And still, this fragment is undecidable when we have both quantifiers. So quantifier alternation. Then Julia Robinson showed this in 1949. And much later on, this gentleman here, Leonard Lipshitz, showed that if we only restrict to existential formulae in this fragment, then we have a decidable fragment. So basically, that means that we can solve systems of constraints, of divisibility constraints, because of the existential. And this we can do. And of course, the Presburger arithmetics, when we have only addition as the only symbol, so we don't have multiplication at all, nor divisibility, nor anything else. And this is decidable, and it's known since 1929. So, yes.
So you could also extend arithmetic to be predicate being a power of 2.
Yes.
So does that fit into this picture?
Well, yes. I didn't talk about it because I'm not going to use it later on. But if you have, so if you have addition and the function power of 2, which is more than having just the predicate, yeah. So you have a function that sends x to 2 to the power of x. Yes. Okay. This is still decidable. Okay. So this. So instead of having a multiplication, you have this send x to the power 2 to the power of x.
Which is equivalent to a test.
It's not a test. It's a function. So it computes the 2 to the power of x function, yeah. And this is decidable because if you only have 2 to the power of x, you cannot express multiplication.
So with quantifiers, you get the inverse logarithm?
It's decidable with all the quantifiers, all unrestricted quantifier prefix. But your question is 86 result. It's much later. Semenov 86.
If you add divisibility?
Divisibility, well, it's here. So it's divisibility. Normally, it's undecidable with all the quantifiers. Yes. So unrestricted quantification is undecidable, but existential is decidable.
With power of 2 also?
No. Well, this is open, I think. Plus divisibility and power of 2, I have no idea. Okay. So I believe it's an open problem. Okay. So why are we interested in first order arithmetic? It's because that may help us to verify infinite state systems. So one class of such systems are the automata with integer counters. So finite control automata with integer counters, extended automata. There were some results. So there is this result in '98 saying that if the control structure of the automaton is flat, I'm going to get back to this. Flat means there are no nested loops in the control structure. Yes. So if we have this, and we have some transition relations which are sort of simple. So things like x gets y plus a constant and things like that. Those are affine transition relations. So if those two conditions, flatness and affine, are met, then the reachability problems for this class of counter automata are decidable, meaning that a certain control location is reachable. That's decidable, and this has been shown by reduction to Presburger arithmetic. So one application of Presburger arithmetic was this. We showed later on, actually, the paper appeared in iCalp 2006, and we showed that if we have flat control structures and the transition relations are a little more complicated, so they are parameterized affine transition relations, meaning that x can get x plus a parameter, then we can still decide, but we need to use more powerful theories. So Presburger arithmetic is not enough. We need to use divisibility and even Diophantine systems. But this is something I'm not going to get into too much. And the topic of today's talk is programs with dynamically linked data structures. So it's important to sometimes to reason about sizes of data structures also, not only about their shapes. So the main difference now with shape analysis is that shape analysis will talk only about the topology. So we'll say this data structure is a tree or a list, or it would have some topology, some given topology, but would not tell you anything about how big those structures are. And we are trying to express and decide properties that are relative to the sizes of the data structure. So say like the sum of the length of two lists will be equal to the length of the third list and stuff like that. So we have done some work on programs with lists and also with trees. Both appeared in papers this year. So this is CAV, now 2 days ago. And this was TACAS. And we have some work that I'm going to talk, even more recent, that I'm going to talk about it today. So this is submitted work. Okay, so first part of the talk is now about decidability results in the theory of addition and divisibility, so first order integer arithmetic. And the second part of the talk is going to be about programs with lists and reachability problems. So first we just do arithmetic. Okay, so I said before that the theory of natural numbers with addition and divisibility predicates is undecidable. And here is a short proof of why this is undecidable. It's not the original proof of Robinson in '49. It's actually shorter. And it's based on Hilbert's 10th problem. Well, in 49, Hilbert's 10th problem was not known to be undecidable. That's why Julia Robinson, who was actually working on Hilbert's 10th problem for quite a long time, she could not use it at that time. So she had an alternative proof to that. But now we know it's undecidable, and we can use it as the undecidability argument. So this is the original statement of the problem as given by Hilbert. So it says basically that once we have a system of polynomials, yes, with integer coefficients, it is undecidable to know whether this system has an integer solution. Okay, so we have integer coefficients, and we're looking for solutions over integers. And the simple fact that a solution exists, so the problem that asks whether a solution exists, is undecidable.
What does a Diophantine equation look like?
Yeah, so the Diophantine equation is exactly this equation with integer coefficients.
Okay.
And we're looking for integer solutions.
So linear, the variables are
It can be a polynomial, not necessarily.
Like 3xy plus 4x squared plus 3x cubed is equal to 0.
Yes. And so since you have used only integers and you are looking for integer solutions, that makes it Diophantine. Yes. So I think so. It was Diophantus, a Greek mathematician, ancient, brought up this problem. So okay. So we know this is undecidable, and we're now going to use this fact. So let's see what we can define now using divisibility. So first of all, we can define the least common multiple relation. So we say that z is the least common multiple of x and y. If for all t, if x divides t and y divides t, that implies z divides t. Yes. So that in one direction, that means t is a common. So any common multiple of x and y is a multiple of z, yes, and the other direction shows it will give us equality. Okay, now this is This is actually a definition used by Robinson in her paper in 49. So now we have defined this relation. Now what can we do with it? We can define the perfect square relation. So we can say that y is x squared if and only x. This holds. Why? Because we have x and x plus 1 are relatively prime. Yeah. So the least common multiple of two relatively prime is their product. Yes. So now the product of x and x plus 1 is x squared plus x. So that brings x equals x squared plus x. So y equals x squared. Okay. So little high school arithmetic. Okay. Now. Further down, we can now define multiplication because we have perfect squared. So if we compute this, yeah, so that will give us 4 times x multiplied by y. Yes. So if we say that 4 times z equals this, that will get us to z equals x multiplied by y. Yes. So then multiplication can be actually defined. Yeah, if we do all the replacements, we can define multiplication using divisibility and one universal quantifier. Yes, which is this one here. And that means that once we have defined multiplication and we have addition, then we can express any Diophantine system using only those two operations, right? Because all we have is multiplication. And this problem now it's undecidable. See, we have okay. So everything here is existential. So if you take any Diophantine system, you can write it using those forms. And the only universal here will appear in this least common multiple relation. So that means that only one universal quantifier can make the class undecidable. Because we also know that divisibility purely existentially is decidable. But since here we have one universal quantifier, that already makes the whole class undecidable. Yes, because this proof works for only one quantifier. Okay. So now let's look at some fragments that are decidable. So let's first consider the following fragment. So we take any formula that you can write that we can write with addition and divisibility. We put it in prenex form, meaning that we put all the quantifiers in front of the formula. Yeah. We rename variables if necessary. So we have, if we have this prefix of quantifiers at the beginning and no quantifiers after that, then we just cut the prefix somewhere. So we have a green part and a purple part, yes? And our condition is that any divisibility predicate has green variables to the left and any other variables to the right. So meaning that the purple variables can only appear to the right, yes? This is how we define this class. It's actually well, we came up with this for this FOSSACS 2005 paper, and now we studied this class, and we found that anyway it's undecidable. Even with this restriction, it's undecidable. But one decidable fragment is if we only have one variable on the green part. Okay, so having one variable to the left of the divisibility sign, that will makes it this.
These could be arbitrary quantifiers, existential or forall.
Yes, all of them. Yes. Okay, so.
What is the intuition for studying this one?
Well, it came from list programs, in fact. Now you will.
So do you have quantifier elimination procedure?
Yes.
So in that case, can't you alternate the green and the purple?
It will not work. So our procedure will only eliminate the purple ones. And
right, but
yes.
Oh, it will only eliminate the purple.
Yes. So if you alternate, it's not the same. I mean, it's not. It will only work for the purple ones because the purple ones are to the right of the sign. You will see in a minute why.
And
so what are you with? So different question. So I'll wait.
Okay. Maybe the next slides will answer. So here are some ideas. Okay. Okay. So this is okay. There are two results we need to use. We need for quantifier elimination, and this the first one, the Chinese remainder theorem, is used to eliminate the existentials. Okay. So the Chinese remainder theorem says that this is an equivalence. So whenever we have a system of divisibility constraints over some linear terms here, we can eliminate the existential variables that are in front. So whenever we have some x's here, a system of constraints with x's, we can eliminate them. But what we get instead is some GCD terms, greatest common divisor terms. So if you look at on the right hand side, there are no more x's, but there are some constraints between the coefficients, and then those appear in greatest common divisor terms. Okay. So let's just have a look at an example. Okay, if you think of how to prove this uses Euclid's algorithm, but it's a known result.
What is paren ai mj comma ajmi?
Sorry.
Paren closed.
Where?
What does that notation mean? I forgot now.
Where?
This notation. This pair.
It's the greatest common here. AB is the greatest common divisor. Okay, so it's of A and B. So here is an example. So you have those two equations here, and there exists x that satisfies them both. Okay, so there exists x such y divides 4x plus 12 and y divides 12x plus 3. Now, if we just apply this blindly, what we get is a constraint on y that will not involve x anymore. So we have eliminated x, and we get those constraints. Now, we have to look at some ways of simplifying those constraints, and in fact, you can see some simplification here. Here I just pulled 4y because the GCD of this is 4y anyway. And that means that y has to divide 33. And this is true because the GCD of y and 4 is a divisor of 4. And any divisor of 4 is a divisor of 12. So this is trivially true. Yeah, we can take it out. So what we get is y divides 33 and GCD of y and 12 divides 3. And from here you can think of what are the values of y. It's an easy exercise. Okay, so the whole idea anyway here is, without getting into too much technical detail, is that you can eliminate x from here, whenever we have some system of constraints like that, and what we get is GCD terms. And now a way of dealing with GCD terms. We normally don't want to eliminate variables and introduce a new operator in the logic. Yes, so we have a way of we need a way of eliminating those GCD terms. So here is how it works. So we have let's take something like this. So we have GCD of f and g, and now we have supposed that on the left of the divisibility sign we have only one variable. That was the z variable. Okay, so then you can use the fact that the GCD of f and g is the GCD of f and r if f. Okay, so if you divide f to g using polynomial division, you get some remainder. Yeah, it's either f is bigger, then you get a remainder, or from g, or g is bigger, then you get a remainder from f. It's either one of the two cases. Yeah, but in either case, you can replace the smaller one by the remainder. Okay, so in fact, the GCD of f and g will always be equal to the GCD of either f and the remainder or g and the remainder. Okay, so now you eliminated one linear term and replace it by a constant, because this remainder is a constant now. And if you have a constant here, you can simplify it further. So you can use that f is equal to some remainder modulo the constant, yeah. And this remainder is of a finite set, so you take it from 0 to c minus 1, yeah. And then you replace the whole GCD term by the GCD of the remainder and the constant. So it's a GCD of two constants now, and this can be computed. So then everything boils down to a Presburger formula in the end. Okay. So this is how we eliminate GCD terms. Okay, so now what we have done up to now is how to eliminate the existential quantifiers. Yeah, but then we will have universal quantifiers. So yeah.
So far as if you have an existential quantifier prefix, then you got completely rid of that extended divisibility, and you're left only with constant divides.
Yes, which is Presburger, because if a constant divide, yeah. So in fact, we can we can eliminate it, and we boil down to Presburger. And the idea is that the whole thing will boil down to Presburger in the end. That the process of elimination is non-trivial. It will cause some blow up. I should have said that in the beginning. So in fact, when you have, maybe I can just go back a little bit. So when you have only one variable here, yeah, so this is the whole idea. So L of 1, when you have only one variable here, actually is equivalent to Presburger. So this is what I'm showing now. Okay, so this is how you eliminate existentials. And how we eliminate universals now, because we might have universal and then some disjunction. So we use this conjecture that was proved in '69. I think it was announced by Erdős earlier, and he offered $25 to whoever can prove it. So the conjecture is something very simple. You have n arithmetic progressions. Yes. So if you look at the picture here, you have 3 arithmetic progressions. Yeah, an arithmetic progression. So it would start at some base, yeah, at some integer, and then it will progress using a period. So it's something a plus b of x for any x. Yes, so periodic sets of numbers. So you have the red one. See, it starts, I think, at 1, and it progresses with 2. You have the yellow one, it starts at 2, and it progresses on 3. The period is 3. Then you have a red one, starts at 1, and I don't know, goes with 2 or something like that. Anyway, the whole question is, when we are given such a set of n arithmetic progressions, when do they cover the whole set of natural numbers? Yeah. So take the union of all. Yeah. There might be overlappings. We don't care. The question is to cover the whole set of natural numbers. Yes. And the lemma says that this is true if they cover the first 2 to the power of n numbers. Yes. So n was the number of arithmetic progressions. And now we have to go up to 2 to the power of n. So if we manage to cover this finite prefix, that this lemma will tell us that we will cover the whole set of natural numbers. Yes. So this now very very simply applies here, and we can eliminate universal quantifiers, right? So whenever we have this disjunction now is the union of arithmetic progressions. So if this disjunction is true for all the x's, yeah, so that the whole set of natural numbers is covered. In fact, this is the same as covering up to 2 to the power of n. So we take the conjunction now of the first 2 to the power of n elements. Yes. So we have replaced this for all x by some finite conjunction.
I don't see where are the arithmetic progressions in the formula below?
Here. So each bi divides x minus ai.
Okay.
Now this is an arithmetic progression because why? Because if you can I write it here?
Okay. Yeah.
Okay.
Yeah,
okay. So you have b divides x minus a. That means that there exists some k such that x minus a equals b times k. Yes.
Okay.
Okay. So now if you take the set, so x, x is b times k plus a, okay. So then this means that x belongs to the set a plus b times n. Yes, okay, it's the same. Yeah. So that means that here we have the progressions, and the coverage is in fact that. This should hold for all x. Yes. So, okay. So this will eliminate universal quantifiers, but only from this restricted formulae. Yeah. So what's restricted in here is the fact that you did not have negation. Okay. So now imagine we had negation terms. And then we have to do some generalization. Okay, so the generalization, in fact, says that now n progressions instead of covering n, will cover another progression. Okay, so you can think of the set of natural numbers as a trivial progression. Yeah. So instead of asking the question whether n is covered, let's ask the question whether a given progression is covered. And in fact, the result is the same. So this is the case. If and only if the first 2 to the power of n elements of the progressions or the progression are covered. Okay, so given this, now we can do negation. So let's take a formula now that's a little bit complicated. It has negation here, so it has some positive terms, divisibility terms, and some negative ones. And the first thing we do, we take negation out. And we transform this disjunction into a conjunction. So okay, so it's a negated conjunction, and now this disjunction here will become an implication because it's a disjunction of something that's negated with something else. So this is the same as saying that a conjunction implies the disjunction. Okay. Right. And this should happen for all x. Okay. So now, if we look at the formula on the bottom, the first term here is in fact an intersection of arithmetic progressions. Okay, so every little term here is an arithmetic progression, but what we have a conjunction, so we have an intersection. So now an intersection of arithmetic progressions is an arithmetic progression itself, because you take just the common points. Yeah, it will be a progression, and in fact the period of the progression is the least common multiple of the other periods. Okay, because they have to meet once in a while. So take one that has period 2 and the other one that has period 3. They will always meet after 6. Yes, and so this is the first arithmetic, which is the one that has to be covered is here, right? And the other one has to cover it. So now how can we eliminate it? So we say okay. The first one here is the vacuity condition. So this is true. Okay, whenever the first progression is empty. So whatever the first formula is here, the intersection of those might be as well empty. So if this is the case, then we can write it like this. So there is no y such that this is satisfied. Okay. So that means if the first set is empty somehow, then it's included in the second set. So then the implication is true. Otherwise, the condition is non-vacuous. So we have some y that belongs to the first set, and then this is covered. Now the progression that starts with this y, okay, and goes by the period that's least common multiple. Now this is covered by the second one. So what we used here, so we eliminated x, we replaced by a finite conjunction, and the period now is the least common multiple. This horrible thing is the least common multiple of all the periods here, but those okay. So this is the coverage condition. Okay.
So let's try to
yes.
parse it.
Okay. Yeah. Well,
so the middle line. So you have x1 and x2 that satisfy the antecedent.
Yes.
Right. So therefore, x1 and x2 have to be satisfied by something in the subsequent.
Yes.
So it's non-vacuous for both x1 and x2.
Yes.
But in your reduction, you only have the requirement that there is a single x1.
It's enough to have only one.
Right. And the reason was?
But I mean, okay, it's enough to have only one because you are dealing with periodic sets. I mean, if you have two, they must be separated by a period. So either you start with x1 or you start with x2. In the end, you will get to the same to the same thing. So the same condition. So the only the thing is here. Okay, here. This is a disjunction, so meaning it's either vacuous or non-vacuous, right? Oh, sorry. And now if you look only at the vacuity test, so this still has we haven't got rid of the universal quantifier, but now if we push the negation, yes, we get universal quantifier on y, but we have no more negation. So our goal was to eliminate negation. So now, if we don't have negation anymore, we apply the simple version that was on the first slide.
You don't need to push the negation in the first case. You could just eliminate it by using the first slide.
Yeah, exactly. Yes. Or yes. Oh, well, okay. Actually, no, I'm sorry. Here, no. I said something that was not true. So this negation, no, you will eliminate the existential now. Okay. So you use Chinese remainder theorem, eliminate the existential then let negation be there, and it will not hurt. Okay. Okay, so just to fix the ideas a little bit. So now this set here becomes decidable with only one variable on the left. And this is just, okay, I will not go into details anymore. This is the formulae we start with. Okay, so we start with some formulae that will have z on the left. In fact, we consider open formulae because z can be quantified any way we'd like. But if we just take an open formula like this, we will eliminate all the quantifiers starting with xn and going, with the innermost one, we eliminate it, and then the second one, and so on. And the result that we get can be translated into Presburger arithmetic. So this whole formula here, in the end, will be equivalent to a Presburger formula on z. Okay, an open Presburger formula on z. And then you can quantify z any way you'd like. You'll have equivalence, and if you quantify over z, then you're still Presburger, so you can decide if it's okay, if it's decidable or not. Okay, here there was some example. Okay, I can go through that. Maybe that will clarify a little bit. So we take this open formula here on z, and the idea is let's define the set of all z's that will satisfy the formula. So let's find z that this is true. And okay, I already put the formula using the implication, so it's already good. It's already for applying Erdős lemma. So we apply it once here, and we eliminate the innermost y, or at least we try to eliminate it. So here is the vacuity condition, the first one. And then this is the non-vacuous condition where you have there exists some y, and now you had only one consequent here. Yeah, so we had that this periodic set had to be covered by one periodic set, which means that it's enough to cover only the first two elements. Yes, so those are the two elements are here. So this is the first one, and this is the second one, and this is okay. This is the periods that we computed using this list common multiple, and now this can be simplified as follows. So right, so we first eliminate y using Chinese remainder theorem. From here, we get to something that is true. Yes. So this happened before. So the GCD of z and 4 then is a divisor of 4, which is a divisor of 12, which is trivially true. Now we have negation, then we get to false. The whole thing disappears. Okay. And now another simplification is that if we have this, so we have this, we consider the first term here, then the second term mainly boils down to saying that z divides 12z divided by the GCD of z and 4. And this will always be true as well. So that means that the second term is not necessary. We can eliminate it. And now all we get is all we have is the two terms and the existential. So now we apply Chinese remainder once. We get something like this. And in the end, you'll see the solutions for z. So in the end, what you get is z has to divide 33x, and the GCD of z and 12 divides 3x. So now this should happen for all x. Yes. So then it should happen for x equals 1. That restricts z to this set here, because all the divisors of 33 are 1, 3, 11, and 33. And now you try them all with 12, and they will work. So why they will work? Because it's either 1 or 3. Yeah, this GCD of z and 12 is either 1 or 3, and this divides 3. So no matter what x is, this will be true. So then this is our solution. Okay, just an example on how you can apply this this theory. Okay, so now let's look at the application. So if you're left with if you don't remember all the technical details, at least one thing that should be remembered from the first part is that first of all, the theory with the least common multiple is undecidable, so because of Hilbert's tensor problem. And the second one is that once we have only one variable to the left of the divisibility, that is decidable. So those are the two results that will be used, okay, in what follows. So now we have problems with lists. Problems of programs with lists. So we consider programs that are sequential, non-recursive, and they use data structures like this. So you have lists, you have maybe some data. For now on, we don't really care so much about this data here. And we have a next successor. So every memory cell will have a next successor. And we are interested in two kinds of properties for this class of program. So safety properties, saying that given any input to the program, whenever we reach a certain control location, then a certain property will be satisfied. This is like having assertions in the program, right? And the termination simply says that for any given input, the program will terminate. Yes. So those are maybe a little non-standard because we consider open programs with input, and we like to find out answers about any given input. Okay. Whereas in the classical sense, safety and termination would be for closed programs. And this is the main difference. Okay. So what's in our programs? We have pointer variables. They range over memory locations, yes, as usual. Then we have assignments on pointers. So assignments can set pointers to null. They can allocate new objects. Then they can assign pointers between them and create next edges between objects. Yes. So like this one actually erases a next edge, and this one creates a next edge. Then we have conditionals. So we have while and if constructs, and the guards are just pointer equality. Or in fact, you can have Boolean combinations of pointer equality. So this is all very standard. I mean, you can write things like this in C or in Java, and And we have assertions for safety. Okay. Now, two remarks on the syntax. So those two assignments here are called destructive updates because what they do is they either erase or they add some next pointer. So they will modify the structure of the heap somehow. If you have programs without destructive updates, and we will consider programs without destructive updates, then basically those programs will move pointers along the heap structure but will never modify the edges of the heap structure, right? So those are the only ways you can actually modify the edges on a heap. And second remark is flatness. Okay, so let me get back to flatness. So if you look at the control flow graph of the program, flatness means there are no nested loops, which syntax-wise, that means that you don't have while or if constructs inside the body of the while. Yes. So why we will, because if you impose the flatness condition, that greatly simplifies the structure of the class of programs that you consider becomes very, very simple with flatness. It's something related to decidability. So okay, historically, let me say, if you take a counter machine, okay, and you don't have the flatness condition, then the program is the problems are immediately undecidable for that, because you think of the two counter machine only. So you have a two counter machine with increment, decrement, but complicated control structure. Then it's Turing powerful. Yeah. Make it flat, it will become very easily undecidable. So decidable, sorry. And now our question is, what happens now with programs with lists if we have the flatness condition? Because if we don't have the flatness condition, any program with lists can simulate a counter machine very easily. You just each counter is simulated by a list, yeah, Increment, decrement are just adding elements or erasing from lists. And without the flatness condition, this will straightforwardly be an undecidable model. Yeah. So in fact, this model with lists is Turing powerful. Now the question is, what happens if we simplify it? So in fact, we will consider only programs that are flat and have no destructive updates. Okay. So we impose two very hard conditions on the programs, and we'll still find out.
It's still undecidable.
Yes.
So even if you have a single list, then also it becomes hard.
So singly linked lists.
No, only a single list in that type of.
No. So I'm going to get back to that. So yes. Okay. So we will see where the difference comes. But okay, those are the heaps that are manipulated by programs with one selector. Okay. So you see, you have program variables here. Each node is an object. Yes, and each object has one next field, so one successor. Okay. So then heaps will look something like this. You can have sharing between lists, and you can have cyclicity. But you cannot have divergence. That's the only restriction. And once you have this, now we are trying to make some abstraction of those structures. So first of all, let's notice that you have some special points in the heap structure. So those points are either directly pointed to by some program pointer, or they are joint points. So they have two predecessors or more. So for instance, here we have program variables, but here we have two predecessors. So all of them will be assumed to be cut points. Okay, we'll call those cut points. And now everything that's in between two cut points can be assumed to be equivalent. So all the nodes between two cut points, they belong to the same class. And now if the abstraction that we make is that we take the quotient graph with respect to this equivalence relation. So we will replace each equivalence class by one node, one abstract node. Okay, this is something that's being done quite a lot, and so our graph will look something like this now. So we have abstract nodes that correspond to equivalence classes, and since we don't want to lose the information on how many objects were there, we label those nodes by numbers. So the numbers will tell how many nodes were inside the class. First one had 2. Okay, maybe I can go back. Sorry, I can go back. See, the first one had 2 here, and the first one on the bottom had 3. So then you put all the numbers like this. Okay, and what you get is an exact representation of what you had before. Okay, no information is lost. But now you would like to think to reason about infinite sets of graphs of shapes, as it, for instance, as it is the case in program analysis. And one way to do it here is to parameterize. So you have the shape is given, and now instead of numbers you add symbolic variables. Okay, so that means that for each valuation, for each assignment to the x's, you will get a specific graph. So replace x1 by 1 and x2 by 3. First was 2 and then 3, and all the rest like in the slide before, and you will get the original graph. Okay, but now you have a way of representing it, representing symbolically an infinite set of graphs. Okay, so now two kinds of properties. More formally, safety means that if I'm given a program with lists, and the program has some annotations, okay, the annotations will be assertion statements at given program points. Yes. Now the program is said to be safe with respect to a parametric heap. So a parametric heap now is a heap with parameters. Yes. So this is just a symbolic representation of an infinite set of heaps. So the program is said to be safe with respect to this parameterized heap, if and only if, for all instances of this heap, if I start the program on a given instance, then anytime I reach one control location like this, the assertion is true. Okay. So this is just a generalization of the safety property for programs with input, okay, with given input. So we reason about infinite sets of heaps. And termination is just the same. So just replace here this assertion part with assertions by the condition that the program will terminate. So for any given heap in the class, yeah, in the parametric heap, the program has to terminate. Okay? So let's have now those two in mind, and we'll find that both are undecidable. So those are undecidable, as I said, for programs that are flat and have no destructive updates. So what does it mean? I can write only a sequence of while loops, okay? I can have maybe some ifs in between, so I can have branching, but nothing inside the while loops. And moreover, they do not modify the given structure. So you give them some input, and they will not modify it. And both those properties are still undecidable for very simple programs. So why?
Okay, if you also, will the undecidability hold if you forget about ifs also, if you don't have if statements, or you need if statements?
I do need if statements. Yes, I do. Of course, I do.
What if you make the predict non-deterministic?
I'll get to that maybe. Yeah, I'll get to that in a minute. Let's first look at deterministic ones, okay? But deterministic, but with infinite inputs. Yeah, so unbounded. Okay. Okay. So you see here we have so n cyclic heaps. So that means you can have multiple cycles in the heap. Yeah. Of course, when you have at least 2 cycles in a heap with one selector, that means that the 2 cycles will be in different, disconnected parts. But you can still have as many cycles as you want, but they have to be in disconnected parts. So you consider heaps with as many cycles as you want, more than one. Okay. And so the idea to prove undecidability is that you take an input heap, and you would show that some arithmetic relations now hold between parts of the heap. So length of lists encode some, they represent numbers. Yes.
By the way, what is the corresponding undecidability result? Supposing I have flat control structure,
yeah,
and I have input of integers, natural numbers. How many natural numbers do I need to get undecidability?
That depends on what you have on transitions. Okay, so if you have counter machines, if you have affine transitions, it's decidable. Otherwise, it's not.
So with affine transition, it's decidable no matter how many integers you have.
Yes. So how many counters you mean? Yes, yes, decidable. Yes. But this is not quite like the counter machines. So this is we'll see. So so the idea is that now you are given a parametric heap. That means an infinite set of heaps, and you are trying to establish some arithmetic relations between parts of the heap. And once you can do that, you will get to Hilbert's tenth problem. In fact, so this works like this. So we use the complement, okay, of the Hilbert's tenth problem. Why? Because Hilbert's tenth problem is existential. Okay, so it says, I don't know if the system has a solution or not. I don't know if there exists a solution. Now take the complement. Okay, I don't know that for all x's, x is a solution of the negation of the system. Yeah. So just take the complement of this problem. It's of course still undecidable. And we use this complement. So we say that the system S, so for any, given a Diophantine system, yeah, build a program in the parametric heap that describes the input such that S does not have a solution if and only if P, starting on any input, terminates or is safe. Okay. So why we need a complement? Because we need some universal condition. Okay. But still the complement is undecidable, so we'll use it. And now, what's the idea of the reduction? So as you remember, to code Hilbert's tenth problem, we only needed addition and least common multiple. Okay. And now, how to check addition? How to check for addition? So how can we check that x plus y equals z in a heap? So let's consider a heap that looks like this. Okay. We have basically two lists, but the first list is cut into two. So you have a V here that cuts the list into two, yeah? So X is the first part, Y is the second part, and then we have the Z, that is the second list, and they are both disjoint. So now we write a very simple program, so we put I here and J here, and as long as they are both null, they will go, they will advance together, yeah? I have one while loop here, and they advance synchronously, yeah? So if they get, now if at the end of the loop they get both to null, well, that means that that X plus Y equals Z, yeah? Because the length of the first one equals the length of the second one, okay? So now I can make a decision. Either I go to some okay statement, or if it's not the case, I go to some error statement, or whatever. But this is just a piece of code that will allow me to check whether this is true or not, or the negation. So I can check if X plus Y is different than Z by replacing error with okay. Yes.
Where did you use V in there?
V. I don't use V. No, V is just in the input.
So the arrow between
The X and the Y block.
Yes.
That's not the next pointer.
That is
else.
That is the next. Yeah, that is the next.
So the W block doesn't have any next, or only has.
No. It's all inside. So in fact, this is a parametric heap. So now, if you give values to X, Y, and Z, that means that each block here is in fact a sequence of next.
So you have two lists, X and Y, that are appended.
Yes.
And you want to see if the length of those two lists.
Yes. It equals the length of the bottom. Yes.
But I don't think this is, I mean, you have to use V somewhere, right? Because V represents Y. To check that X plus Y equals.
No. V is just in the input. I mean, it's just V is important because it comes after U, in some sense.
Where do you specify in the input that V comes after U?
The input is given. So this is the input shape.
This is the input.
This is the input. Yes. So my reduction builds a program and an input. Yes. But in fact, it's not one input. This is an infinite set of inputs, but they all share this structure. Yes.
Okay. All right.
And describe that input. So
By using that.
But I give the picture. So I just draw I give the graph. The graph is the input.
Indeed.
I see.
But it's parametric.
It is parametric. Yes. So this is the specific. The input specification is a parametric graph. Yes.
Okay.
So I have a feeling that there's this paper by Chakravarti and others in Popper 2002, which can actually do this counting even without sort of deterministic conditional, with a much more sort of much less expressive language.
Which paper is
There's a paper in 2002, probably, I guess.
By?
2003 by Chakravarti.
I don't know.
So that you can do this reduction to a program just manipulates lists without cycles. But you can have even non-deterministic conditions
Okay.
for the undecidability.
Oh,
So the class that you're reducing it to is much more expressive in a sense.
So you should give me the link, because I don't know about that paper, so that would be helpful. Okay, so this was addition, and now how to code the least common multiple. Well, you take a heap now that looks like this. So you have two cycles here, U and V, and you have a acyclic list, okay, W. So now you actually used all the 3 pointers here. So you have 3 pointers that will just traverse the 3 lists, I, J, and K. And so the idea is now each one traverses a single piece of heap, and you will get to the least common multiple when I and J, so the ones that are on the loops, will get back at the beginning at the same time. Yeah. So imagine the first loop here has length 2, the second one has length 3, and you start with the beginning, And when are they gonna come back at the same time in the beginning? Well, it's going to be after six iterations. Yeah. Because after 6 iterations, the first one did actually 3, and the second one did 2. So they meet. Yeah. So this is exactly what we're testing here. Yeah. And we are testing, so the while loop will come out as when they both meet. Yeah. And then you are testing that k, the third list actually got null, because that means that z is actually equal to this period. Okay, so we have now we have the ingredients, and now if you do the whole, I'm not going to enter the details, but now you can actually prove that using those two pieces of code, you can combine them in such a way that any system. There are no quantifiers.
You're going to reduce Diophantine. No.
Yeah, you are given a system. Yeah, so now you are going to reduce the system.
So the system that was undecidable was x plus y equals z and
multiplication. But now multiplication you can code it using the least common multiple. I mean.
Yeah, but the thing is that the original thing has quantifiers also, right?
No. The systems don't. So the systems, they only have existential quantifier, right? Oh. So the system is just a conjunction of conditions and.
So integer arithmetic with existential quantifiers and plus and LCM is undecidable.
With plus and LCM is undecidable. Yes,
right.
Exactly, because of yeah. I mean, you don't use any universal quantifier in order to code multiplication. So you use one universal when you go from divisibility to LCM, but from LCM to multiplication there is no quantifier. It's just. So you can actually write any Diophantine system using LCM instead of multiplication. It just gets bigger, but.
So it seems that you need multiple lists to simulate this.
Yeah, in fact, so very good remark. So now you have, if you have at least two, otherwise if you don't have 2 cycles, at least you cannot simulate LCM. So then for 1 cycle it will work. But there are some. Okay, you can extend a little bit. So. We have given this result for heaps that have a given shape, yeah. But you can also work with arbitrary heaps. So the idea is, so before you construct your gadget, your program, you build a tester, okay. So you build a tester that tests whether the given input has the input has a given shape, yeah. So this can be done also by a flat program. So just test the shape of the input, and also for non-deterministic programs, we can show what the same problems are undecidable if you start with the empty heap. So now the idea is I have a non-deterministic program, and it always starts with nothing in memory, and then what it does is just instead of a tester now you have a constructor. So you have a small constructor that builds the heap that you need, yeah, the shape that you need. Since it's non-deterministic, in fact, it can build anything of any length, and it's the same result. So the same results will hold. Okay. So now for 1 cycles or no cycles or 1 cycles. Okay. So those are decidable now, and what's the intuition now? So now I'm going to talk about counter machines a little bit. Hopefully not too much. So the idea for decidability is that you can build, given the program, you can build a counter machine that has a special form, so it's flat and it has some simple transition relations, and we know the counter machine is decidable. So then, if the counter machine will simulate the program one to one, yeah, then all the problems that you ask for the program will be true on the counter machine and vice versa. So if the counter machine is decidable, that means the program is also decidable because of the one-to-one correspondence between their semantics. And so what is a counter machine now? We have a set of counters, yes, a set of variables. We have a set of control states and an initial state. and we go from one control state to another whenever there is some arithmetic relation between counters. So this is a general definition. Yeah? So whenever x prime is the set of counters as at step q prime, yeah. So whenever this relation holds, you can move from q to q prime, yes, with the corresponding values. So now, of course, a run of such a counter machine will be a sequence and of configurations, and each configuration has a control state and a set of values. Yeah. So you go from one configuration to another using rules like this. Okay. Now, the problems that we ask for those machines are reachability problems. Yes. So.
We should wrap up in 5 minutes.
Yeah, it's okay. Yeah, I think I. So the reachability problems will ask whether a given state is reachable or not, and this can be done if we can define the input-output relation. So, assuming we have an input-output relation in n steps. So, just suppose you have one loop here, okay, and R is the relation on the loop. Then Rn is the relation between the input values and the output values after n iterations of the loop. And then, of course, this you can generalize to the whole transition relation. And R star is the relation in any number of steps. Okay. So if we can define R star in a decidable logic, then we can decide the reachability questions. Okay. So this is known. So this is a class that is decidable that we use. So we have flat control graphs, and the transitions are of these forms. So we have some parameters. There are no assignments to the parameters, and then we have counters, and then we have guards and actions. Okay, so guards will test the parameters, and actions will update them. And the guards are just combinations of linear and divisibility constraints, yes, between parameters and counters. And actions are just reset, copy, and increment actions. Okay. So this class now, we can show that it's that is decidable. And in fact, the reason it's decidable is because the R star here can be expressed in the divisibility subset with one variable to the left. Okay. Okay. So in fact, this is the reason why it's decidable. So it's not trivially Presburger. It's well, no. In fact, we can have decrement operations. We can have any integer here. It's you're right. It's not. It was not important for the encoding, but you can have. Now, okay, how we simulate the program with lists using this? So we assume that we have we have a heap, and here in the beginning we have roots. Okay, and now the other variables that are not roots, they are encoded by roots. So for each variable, the encoding says which is the root, and what's the distance from the root. Okay. So for U1 you have R1 and delta 1 here, and for U2 you have R2 and delta 2. And this is enough to encode one state because now the structure doesn't change. So we said that there are no destructive updates. The structure doesn't change. So now every move of the program will be an update of those pairs here. And this is all we need to simulate the program. Yeah. So how do we do assignments, for instance? Let's say you have UI and UJ. Those are the roots and the deltas. And you have UI takes UJ.next. Yeah, so UI gets here. So simply you put you update the root of UJ, and the distance becomes delta J plus 1. Okay, that's why we only have increment, because you cannot go back. Yeah, and this encoding now you see is deterministic. So for each, so if you take a flat program, what you get is a flat program. On the other hand, if you take a flat program, what you get is a flat counter machine. Okay, so a little bit more complicated is to encode the guards. So now pointer equality. If there are no cycles, this is just a Presburger. Well, yes, it's just a system of linear inequalities here. So you can encode it like this. So if I was to parse it, so here ui has distance from the root. So the root of ui is ri, the root of uj is rj. The distances are yi and yj. So if those have to be equal here, then it must be that yi minus x1 is greater than x3. Wait, no, it's less than x3, right? Because they have to meet here on this segment here. The same for the other one, and the the differences have to be equal. So this the distance from this point to the beginning of the segment has to be the same for both variables. So that's why you have here this one, yeah. But if they meet on some cycle, okay, so then you have to have some divisibility constraint, because then you don't know how many times this cycle has been traversed in order to meet, for the two variables to meet. So whenever you have a cycle, then the period of the cycle has to divide some constraint, some linear term. So this is essentially why we need divisibility, because otherwise you cannot express, in general, you cannot express guards, pointer equality. But if you have acyclic heaps, then you don't need them. Okay, so basically now, okay, this resumes the result, because we show that the programs can be simulated by counter machines. Counter machines are decidable because of the divisibility theory, and that shows decidability for the two safety and termination for those programs. So again, the message is that if you take more than one cycles in the heap, programs are undecidable. Otherwise, they are decidable. So this concludes my talk pretty much. So I have so we have studied this logic of integer numbers with addition and divisibility. In general, it's undecidable, but if we separate variables according to whether they are on the left or the right of the divisibility sign, then there are decidable fragments here. And we have applied this theory to verification of singly linked list programs. And again, if we have more than one cycle, it's undecidable. Otherwise, it's decidable. Okay, so that concludes my talk. Thank you very much.
Any questions for Raghu? I guess we already asked about.
Yeah.
Yeah, I spent my...
Finished.
You have had your quota.
I had my quota.
All right. Well, let's thank the speaker then.